Hello, stats class. Here is lesson 7.1b. And 7.1a was weird. It was all Desmos. And 7.1b we'll get back to a little bit more of the normal procedure with video notes. And we're going to start with something that was in that German tanks example, statistic versus a parameter. Leave yourself a little room because we're going to make two columns here. And what's interesting is I hope that I've defined statistics so far. We've been doing this class that's called statistics, so I don't know if I've mentioned what it means, but I hope that I did. Statistic is a numeric summary of the sample. Basically, it's something about the sample or a number calculated from the sample. It can be calculated from sample data. And we have done a lot of different statistics so far in this class. And that's why this class is called statistics. We've calculated means and standard deviations and IQRs and all kinds of other things. And we're going to expand that a little bit and say what we're usually doing is calculating from the sample so that we can learn about the population. The parameter is always about the population. And we usually don't know the parameter. It is unknown unless we do a census, which has got all kinds of problems involved. We may have talked about that before. And remember, a census is data about the whole entire population, and usually that's not what we're doing. But usually what we want to do is find out something about the population by calculating something about the sample. So the statistic can be used and will be used to estimate a parameter, because the parameter is usually what we want to know. So that parameter could be a lot of different things. In the German tanks example, the parameter was the total size of the population, or capital N, and we experimented with different statistics that could be used to estimate that. It's not necessarily just the one that matches. So population size can't really be estimated by sample size, but it could be estimated by some other things. Or other times we'll use one that matches. Like if we want to know the mean of the population, we would use the mean of the sample and things like that. Before we go on, a little bit of highlighting. Notice the P matches the P in population. It makes me so happy that it does that. And the S matches the S in sample. So statistic always goes with sample, parameter always goes with population. The same letter thing will help you remember that. And then when we're naming these things, you already saw the lowercase n versus uppercase n, and that could happen with other things too. So usually a statistic is named with ordinary letters. Sometimes with symbols attached. And so, for instance, you've seen X bar before, which represents the mean of a sample. You've seen S before, which is the standard deviation of a sample. And you've seen, we haven't done a lot of them, but we will do a lot more, especially in chapter 8. P hat is the proportion that goes with a sample. And then those have corresponding symbols that are used for the population. So I'm going to make some arrows that go over here and say this is the mean. This is the standard deviation. This is the proportion of what proportion of people say yes, or what, whatever proportion we're looking at. And all of these are named, when you're talking about the population, you use different symbols for that. Most of the time we use Greek letters to represent population values or parameters. And you've seen a little bit of that before, because I've already introduced you to mu, which is the Greek letter M, It is used for mean. The mean of the population is mu. The mean of the sample is x bar. Standard deviation is sigma, which looks like that. That's mu. That's sigma, which is the Greek letter S, and it means the population standard deviation. What's interesting about proportions is we ought to, in fact, some books do use the Greek letter for P, and if we were in class, I would ask you, do you know what that is? And I'm going to put it over here. It's pi. Some books use pi for this. Our book does not use pi, and I think it's because pi means something else. It means 3.14 and so forth that's used in geometry. So our book uses the regular letter P for a population proportion, and they use p hat for the sample proportion. So, but it's not wrong to use pi. If you want to use pi, you can. And some books do that. These two right here and right here are the two most common, and we're going to spend a whole unit on each of them. But not chapter 7. Chapter 7 is all the different ones put together. So that's your basic introduction to what is a statistic versus what is a parameter. We're going to use statistics to estimate parameters. And this chapter is all about the math behind how that works, which is the sampling distribution. And that's what we're going to talk about next. You saw a little bit of that in the warm-up, and we'll do a little bit more now. So let's draw some graphs. In fact, I'm going to have you do 3 columns for this next part. We're going to start with a population. And then we're going to talk about taking samples from that population. And then we're going to talk about taking the samples and making them into a sampling distribution. Because I would say that's the most important thing this week is what is a sampling distribution? Notice that's the title of the lesson in the book. What is a sampling distribution? And so the German tanks thing was supposed to introduce you to that, and today I'm going to try and make it as clear as I can. Let's draw some pictures of what might happen, and let's start with a population, and we're going to put a lot of dots. Make a lot of dots. In fact, they don't even have to be lined up in nice, neat little columns. Just imagine a large number of numbers. And, you know, I don't care if it is, well, the one I drew is kind of uniform, which is about the same height all the way along, but they wouldn't always be like that. They might be normal curved or skewed right or skewed left or something like that. But anyway, that's our population. And imagine we have some numbers on this x-axis, and somewhere in the middle, right here, is the mean. That is the population mean, which is the parameter. And if we actually knew all of these numbers, we could take them all and add them all up and divide by capital N, which is this population size, and we could find mu. But most of the time, we will not know all of that. So what we do is we take a sample. So let's say this one's in my sample and this one, and just pick a few dots. I'm going to pick 5 and say, let's say those 5 dots are my sample. So I'm going to take these 5 dots and make a sample out of them and draw the graph of that sample. Each of these dots is an x value. In fact, I could have drawn x's for every single dot. I'm going to do that over here. I'm going to say I have 5 x's. I didn't really leave room, so let's do that. I have 5 x values that were taken from the population, and they are my sample. And the average of those 5 values is not called mu, it's called x bar, and it's somewhere near the middle one. Not perfect. So x bar is the sample mean, which is the statistic. And it would be the sum of those 5 values added up and divided by 5. Okay, we've done that before. So these little guys, these dots and these x's are individual data values that came from my population, but they're not the whole population. They're part of the population. This is part of the population. This is the whole population. Now, if I want to do a sampling distribution, I'm not going to graph these, and I'm not going to graph these. I'm going to take the x bar from this sample and the x bar from a whole bunch of other samples and plot those. So it's kind of like data about data. It's kind of weird. If I take all of these sample values and find the mean and plot it, That's an X bar value. And then if I took a different sample of a different 5 points, and I could do this, and I could find the mean, and I could plot that, and maybe it's a little higher, and I could do it again. I could do that as many times as I want and get lots of different sample means, and as you may have figured out already, sometimes they'll come out the same, and sometimes they'll come out different, and I could do as many of them as I want. It doesn't even have to be the same as the sample size. I'm going to add a few more just for fun. Those sample means could also make a distribution, and that is called a sampling distribution. Now, the words are really important. This is a sample distribution. This is a sampling distribution. That ling is important because that means we have each value is not an individual data value. Let's write that down here. Each value is the mean from one sample. And that's why I made you test your formula on the German tanks. I made you test it on several different random samples so that you could see that they don't always come out the same. Sometimes they'll be higher, sometimes they'll be lower. We would hope that the true mean would be somewhere around in the middle. This mean right here is the mean of not the original X values. In fact, we could call this mean X. It's not the mean of the original X values. It's not the mean of a sample. It's the mean of the means. That's crazy. And so that's called mu X bar, which is the mean of all the sample means. And this is where it's getting a little bit one step more complicated than before. Now, if everything works out well, like we hope it will, the mean of the sample means would be a good way to estimate the population mean, because that would mean that these are well balanced above and below the true mean. And that's one of the things we're going to be looking at in this chapter. So let's summarize our vocabulary here. We've got a sampling distribution. What is that exactly? I'll give you the official definition, which also was in the Desmos somewhere, but sampling distribution officially is a distribution of many statistics from repeated random samples. So take a minute to picture this. We have our population, we take a sample, we find the mean. We do it again, we take a different sample and we find the mean. We take a different sample and we find the mean. We repeat this over and over again, and we take all the results of that and plot them on a graph, and that is called a sampling distribution. Officially, if you want to be super picky about it, we would need to get this distribution to be complete, we would need to take every possible sample of that size from this. So if I wanted to be exact, I would take all possible samples of size n from that population, and I would use all of them. That usually doesn't happen unless you're writing a computer program to do that. That might be possible. Most of the time, we're going to do an approximate standard sampling distribution, which means we just do many. But not all. So they may ask you about that in your homework. So I wanted to make sure I told you that if the answer in the back of the book says, no, it's only approximate, that's why. It's because it's not all possible random samples. So now, how do we know if a sampling distribution is helpful or not? Ideally, I told you this already in the Desmos, but just to make sure, ideally, we want the sample statistic, that is this sample mean or proportion or whatever, sample statistic to be a good estimator of the parameter. There's a keyword, estimator of it's redundant, but I'm putting it anyway. I could have just said statistic, and I'm putting the word sample to emphasize what I said up above about samples always have statistics, populations always have parameters. So again, it's redundant, but I'm putting both words just to emphasize that. I could just say parameter and you should assume population. So we want it to be a good estimator of the population parameter. A good estimator has two things that are true about it, and then that is it for today's notes. Two things that should be true for a good estimator, and that is it would have the correct center. That means it would be accurate, or the other word for that is unbiased. Remember, bias means they tend to overrepresent or underrepresent a certain part of the population. So if your estimator tends to be too big or too small, that would be biased, and that's not what we want. We want some of them above the true mean and some of them below the true mean and nice and balanced. So that's the correct center would happen if mu x bar, that's the mean of all the x bars, was the same as mu. Or if we're dealing with proportions, that would be the mean of all the p hats would be the same as p. That's what we're hoping will happen. And actually, the reason these two are the most common is that they're naturally unbiased. As long as you do a random sample, this is going to be true. And we will talk some more of that as we work our way through this chapter. But so that's the first thing, is you want the correct center. That doesn't mean you expect one specific x bar to be exactly the same as mu, because some of them will be too high and some will be too low, but you expect them to be balanced. Some above, some below, not all below or all above or mostly, right? That would be the correct center. And then the second thing that we're hoping will happen is we will have a small spread. And the official word for that is precise. And that means that we just want the standard deviation of all of these x bars to be as small as we can manage it. And we'll be talking again about that as we work through the chapter about how to make that happen and what situations make this happen more likely. But for right now, those are the two criteria that we're going to be hoping for in this chapter. And that is enough for today's notes because I don't want to overwhelm you. We will continue with this on Wednesday with 7.1c.